Good morning students. In the previous class we have discussed what is an equivalence relation and also what is an equivalence class. I am repeating the definition of equivalence class again. Let tilde be an equivalence relation on a set S. We can call this notation also as equivalent. Okay. Then for a given element A element of S, we define the equivalence class of A to be the set of all elements of S that are equivalent to A. That is, the equivalent class of A is equal to set of all x in S such that x equivalent to A. And the collection of all equivalent classes will be denoted by the symbol S bar tilde, and we call this set as a factor set. And also we have discussed what is congruence equivalent classes of congruent modulo n. And in that class, if we consider the relation equivalent as a congruent modulo n, we noticed that the equivalent class of A, equivalence class of A coincide with the congruence class of A mod n if we consider the relation as congruent modulo n. Okay, from congruence class thanne I mari equivalent class of A if we consider the relation as congruent modulo n. Next example is, if given a function f from S to t and given any two elements x1 comma x2 element of S, we define the relation x1 equivalent f to x2 if f of x1 equal to f of x2. Then now we will prove this relation equivalent f is an equivalence relation on S. For that we have to prove three conditions. What are that conditions? We have to prove that relation satisfies reflexivity, symmetry and transitivity. For reflexivity, we have to prove each element in S is related to itself. So let x1 element of S, then we know that f of x1 is equal to f of x1. So using this definition we can say that x1 is equivalent f to x1. So this relation satisfies reflexivity. Now for proving symmetry, we have to prove if x1 related equivalent f to x2, then we have to prove x2 is equivalent f to x1. Suppose x1 equivalent f to x2, then by this definition we can say that f of x1 will be equal to f of x2. Now we can rewrite this condition as f of x2 equal to f of x1, but which is the definition of x2 is equivalent f to x1. So x1 equivalent f to x2 implies x2 equivalent f to x1. So this relation satisfies a symmetry. Now to prove transitivity, suppose x1 equivalent f to x2 and x2 equivalent f to x3, then by the definition x1 equivalent f to x2 means f of x1 equal to f of x2, x2 equivalent f to x3 means f of x2 equal to f of x3. Now using these two conditions we can see that f of x1 is equal to f of x2 which is equal to f of x3. So f of x1 and f of x3 are equal, but this implies x1 is equivalent f to x3. Therefore x1 equivalent f x2 and x2 equivalent f x3 implies x1 equivalent f x3, which implies equivalent f is an equivalence relation. So we have proved this relation equivalent f is an equivalence relation on the set S. The equivalence classes of this relation will be denoted by the symbol S bar f. Instead of S bar tilde, we will denote the set of all equivalence classes of this relation by S bar f, and we will call this factor set as factor set of S determined by f. Next example is, for this we consider A as the set of all integers and B as the set of all non-zero integers. Then consider the set S as A cross B. Then we know that A cross B consists of all ordered pairs of the form sum m comma n, where n will be not equal to 0 because B does not contain the element 0. Okay, so a relation in this set S is defined as Mn equivalent to PQ if M into Q is equal to N into P. This is like the equality of rational numbers. So we know that two numbers 1 by 2 equal to 2 by 4 if 1 into 4 equal to 2 into 2. Okay, like that we can come that relation is defined here in terms of ordered pairs. So ordered pair Mn is equivalent to ordered pair PQ if we can compare this with some M by N equal to P by Q if M into Q equal to N into P, like that. So here ordered pair Mn is equivalent to ordered pair Pq if M into Q equal to the first coordinate of Mn into second coordinate of Pq, that is M into Q is equal to N into P. Now we have to prove this relation is an equivalence relation. For that, first we have to prove this relation satisfies reflexivity. Let M ordered pair Mn element of S. As we know that M into N is equal to N into M, then using this relation, definition of this relation, we can say that ordered pair Mn is equivalent to ordered pair Mn. Okay, instead of P and Q, here M and N is given, so substituting it here, you can see that Mn equal to Nm implies ordered pair Mn is equivalent to ordered pair Mn. Now for symmetry, suppose Mn and Pq element of ordered pair Mn comma ordered pair Pq element of S, and suppose that ordered pair Mn is equivalent to ordered pair Pq, then by the definition we know that M into Q is equal to N into P. Now we can rewrite this relation as N into P, we know that it is P into N. So P into N is equal to M into Q is Q into M. So MQ equal to NP implies Pn equal to Qm. But this is implies, this equality implies ordered pair PQ is equivalent to ordered pair Mn. Okay, so ordered pair Mn equivalent to ordered pair PQ implies ordered pair PQ equivalent to ordered pair Mn. So this relation is a symmetric relation. Now we have to prove transitivity. For that, let ordered pair Mn, ordered pair Pq and ordered pair St element of S. Suppose that ordered pair Mn equivalent to ordered pair Pq and ordered pair Pq equivalent to ordered pair St. Then using the definition we can say that M into Q is equal to N into P, and as P ordered pair PQ is equivalent to ordered pair St, we can say that P into T is equal to Q into S. Now multiplying this relation M into Q equal to N into P with T, we can this equality becomes M into Q into T is equal to N into P into T. But P into T is Q into S. So substitute this, replace this P into T with Q into S in this relation. So we get N into PT is equal to and also replace M into Q with N into P. Substitute M into Q equal to N into P in the left side also. So this relation becomes N into PT. NP into T is equal to N into QS. Okay. Now for proving transitivity, ordered pair Mn equivalent to ordered pair PQ and ordered pair PQ equivalent to ordered pair St implies MP equal to MQ equal to NP and PT equal to QS, just using this definition. Now first multiply the first equation with the T, then this equation becomes MQT equal to NPT. Now multiply the second equation with the N, then this equation becomes NPT equal to NQS. Now so the right side of the first equation is the left side of the second equation, NPT. So from these two we get MQT equal to NQS. Okay, so since Q is the second factor, we know that Q is different from 0, so we can cancel Q from this equation. So you will get MT equal to NS. But this is the definition of ordered pair Mn equivalent to ordered pair St. Okay, so what we have proved is this relation is an equivalence relation on the set S. Now, so this relation, using this relation, we can find the equivalence classes, and you can see that if we compare if we denote ordered pair Mn element of S by M by N, that a rational number, then we can see that this relation, the equivalence classes determined by this equivalence relation is all rational numbers having the same value. That is, in other words, we can say that 1 by 2, 3 by 6, 2 by 4, etc. all these numbers will be in the same equivalence class. That is, actually this relation implies the equality of fractions. Okay. And so the equivalence classes of this equivalence relation form the set Q of rational numbers. Now next example is, let S denote the set of all differentiable functions from R into R. For any fx, q, gx in S, define f equivalent to g if the derivatives f dash x and g dash x are equal. Then we will prove this relation is an equivalence relation. Here the given set is set of all differentiable functions from R into R, and the relation is f equivalent to g if f dash x equal to g dash x. As we know that f dash x equal to f dash x, using this definition we can say that f equivalent to f, so this relation is reflexive. Suppose f equivalent to g, then f dash x equal to g dash x by definition, but which implies g dash x equal to f dash x, and hence g equivalent to f. So this relation is symmetric. Now suppose that f equivalent to g and g equivalent to h, then using definition f dash x equal to g dash x, and as g equivalent to h, g dash x equal to h dash x. So from these two equations f dash x equal to h dash x, but which implies f equivalent to h. So this relation is an equivalence relation, as this satisfies all the three properties to be an equivalence relation. So this relation is an equivalence relation on the set S of all differentiable functions, and we can say that the equivalence classes determined by this relation. In each class the functions, differentiable functions having the same derivative will be in the same class. Two functions will have the same derivative if they differ by a constant. Okay, so in the class of a function fx, there will be all functions of the form fx plus c, where c is a constant. Okay, in next example, let S be the set R square, S equal to R square of points in the Euclidean plane. That is, S is equal to ordered pair x comma y, where x comma y element of R. Now we define a relation x1 y1 related to equivalent to x2 y2 if x1 equal to x2. That is, the first coordinates are equal, then these two ordered pairs are related. Now we will prove this relation is an equivalence relation. For that we know that x1 y1 is equivalent to x2 y2 as x1 equal to x1. Now suppose x1 y1 equal to x2 y2, then using this relation we can say that using the definition of this relation x1 equal to x2, which implies x2 equal to x1, and hence x2 y2 is equivalent to x1 y1. Now suppose x1 y1 related to x2 y2 and x2 y2 equivalent to x3 y3, then using the definition x1 equal to x2 and x2 equal to x3, using x2 as x2 y2 is equivalent to x3 y3, x2 equal to x3. Now using these two equalities, we can say that x1 equal to x3, which implies x1 y1 is related to x3 y3. So this relation is an equivalence relation, and you can see that the equivalence classes determined by this relation contains all the points having the first coordinate equal. All the equivalence classes in this relation will be lines parallel to y-axis. Okay, so all that is vertical lines, so that all the points on that line have the same first derivative. Okay, that is, equivalence class of the ordered pair AB will be just the line x equal to A. Now next is a proposition. Let S be a set and equivalent be an equivalence relation on S, then each element of S belongs to exactly one of the equivalence classes of S determined by the relation equivalent.